lost its IP address. Anybody know what I need to do? Hmm? This guy here runs what we call a DHCP server. And you have to know where your interface card is, by the way, or your interface circuit. We don't have cards anymore. And then what we're doing is we're looking for the MAC address. Y'all remember what the MAC address is? The MAC address stands for Media Access Control, and there's the MAC address. This is the binary address that's built into every device that needs to access an TCP, a network, period. So all your network cards, anything that connects to a network has to have what we call a MAC address. These are unique. IP addresses are logical. They're signed. MAC addresses are physical. These are the physical addresses of network devices in your card. So you can see they're somewhere on your cell phone. You can go into information. I know you can do it on an iPhone and it tells you the MAC address of your phone. So the MAC address for this guy is it's a 48-bit binary number, but they understand binary numbers are real hard to deal with. A lot based today does computer display hexadecimal. The first 24 bits to the left is what we call a manufacturer ID. So this is assigned to the manufacturer. I forgot the group that actually does that. And the other 24 bits would be up to them how they want to assign MAC addresses. So that means the company has 2 to the 48 MAC addresses available to them once they assign that they get assigned the manufacturer's ID. And how many addresses would that be? 2 to 48? That is something on your sheet. So the number of combinations is the number of digits, right, in the base. So 48-bit would be 2 to the 48, and that would give us 40th. Okay, so I remember my calculator. I need to put that in there. So I'm gonna bring up my calculator, and here's y to the x right here. So 2 raised to the 48 means I would have this many MAC addresses available to me. If I ran out of those, then I could ask for another, and we would have that many manufacturer codes and that many MAC addresses available. And this is put in. This is the address that's put into the PLC, your phone. This guy right here has got a MAC address. Everything that needs to connect to a network has this MAC address. So there's a lot of them, but there's a lot of devices out there. Now, once we get that, then we have to click on it, and it's asking me for the IP address. Right now, I'm just going to follow this technique. The only thing I'm going to do is change the last number. When you get it, if you take I don't know, I think it might be in PLC 2 or it's in PLC 3. We'll give you more indication about the IP address and then what the subnet mask is and all that other stuff. But this would be what we call a Class C license. So the only thing I can change is just this last digit up here, which would be the 56, and everything else I'm going to have to put the same. So I'm going to put 169 and then 254 and then 163 and then 100 is the one I've been using. Okay. And we'll hit OK. And then it'll show me when the PLC gets that address. So DHCP servers, what they do is they assign IP addresses. So that's one thing that you do when you go. So your internet service provider has a DHCP server. And as soon as you log in, that's what your computer says, I need an IP address. And what does that thing do? It automatically gives you one that your internet service provider has bought. So they have to pay, they have to lease IP addresses. So it finally got it, so we should be able to communicate with it now. So this is the program I've got in there. And let's go online. I've already downloaded it into it. Okay. So right now I would have to run it. It says my stop button is switch 0. So by the way, this is the way they like to do it over in Europe. They like to put the stop button on the right of the CLN. We usually put the stop button on the left. So here I'm using an examinative close. And I'm using a normally closed switch, and that gets us confused after taking motor controls. Then I come up here, and I can just touch switch 1, and then it seals itself in, right? Standard seal-in circuit. You'll run all over the place. Okay, so what I'm going to do now, and of course down here it says I need to turn on switch 2, and then that one comes in, and then it says output 0. This is a normal close. Okay, so right now this thing is operating. What I'm going to do is I'm going to come down here in my my project tree, which is on the left. And right here we have a force files. I'm going to click on input, and it brings up the data file for the inputs. But notice it's got a bunch of these little dots out there. Can y'all see that? So I'm going to come over here to switch 0. Which would be this. So this is 0, word 0, right? Y'all can see the decimal point, word 0. And I'm going to come over here and make this, I'm going to force this. I'm going to make it a 0. And notice it comes on big red telling me that I turned that thing off. Now my push button, my button is still closed. But what I did is I just forced that input. And we can force outputs. So let's take, by the way, I can put a 1 out there now. So the push button is not controlling that anymore. I'm controlling it with software. The switch is not even into play anymore. I have not changed the position of the switch. If I want to get rid of force, I just come over here and just delete and enter, and notice it turned back into a dot. Now it's under the control of the switch. I can force an output. I'm going to come over to my output table. Here's output 0. Right now it's what? It's de-energized. I'm going to come over here and put a 1 there, hit enter, and it comes up and turns red and says, this is not being controlled by the rung anymore. That output is being controlled by me, right? You understand that? So this is forcing. Now, what could be the problem with this? Well, where could we use this at? Troubleshooting, yes, but if you use it for troubleshooting, you got to be really careful because you just forced an output, and your buddy's out there with this machine, and you just forced an output. So you've taken away every safety feature built into the automated control system. You forced an output. So what you just done? Huh? Or you didn't get that. Yeah, so forcing is built into all these PLCs. Now, basically, you have to build a force. You have to build. Now, what they require you to do is you build a force table. So you can only force the contacts that you put in that table, but you still are going to take away the control of all the safety systems built into that system. But it's great because you might have a PLC over here on the left hand side that you're trying to develop a program for, and you don't have any push buttons to it yet. It's out here. You're just trying to program it. Well, you could simulate these inputs all you want to see if make sure your logic works right. Now that's really great. if you force them if you force them in an active situation, you got to be really careful and make sure that you know the consequences of forcing that thing, right? By the way, a lot of your relays, this came up from relays. So if you come over and look at this, there's a push button on here that I can do. I can force that relay right there. But you got to be careful. I know the guy that got killed. Somebody went down and forced the wrong relay. So they had everything locked out and tagged out. It was in Montgomery Black and they had two hopper doors. It was a furnace, not a pressurized furnace. And they were working on, I think, the top one. And they had it all locked out and everything. And they watched the fluid power work. They went down there and the guy did what? Forced the wrong relay and bottom hopper door. They said they brought him down in 2 pieces. I don't know. I wasn't there. Thank goodness. So forcing, y'all okay on that? On this is very simple, very dangerous too, right? Here it's no big deal because we're not working with systems that's going to kill somebody. But I guarantee out there in industry, you'll be working on some systems where you got clamps and all kind of stuff, and you force those things, it could cause problems. Okay, guys, let's look. I think the next chapter we need to look at is timers. Isn't that right? So what, chapter 8, right? Is it chapter 8? So has anybody dealt with timers before? Where? Microwave, perfect example. Your car's got them all over there, so I leave my lights on my car all the time now, right? And when I turn the ignition off, or when I open my door, right, my lights come on in there. When I get out, when I close my door, my lights over my dome lights stay on just a little while after that, right? Like you said, microwaves, washing machines. Yeah, their timers are everywhere. So do you think they're in industry? Yeah. Where are they? Everywhere, right? That was crazy leg. We'll talk about this. Program contexts that are controlled by a runs output are simply called normally open and normally closed. Examine if open and examine if closed are run contacts that are controlled by an input device such as a switch, push button, and sensor. Everybody understand that? Yeah. So when we're dealing with contacts that's being controlled by a relay or a coil that's in my diagram, we just call them normally open and normally closed. So what we're going to do here, we're going to use look at what we call a non-retentive timer and a retentive timer on delay. What do you think we mean by on delay? You're probably saying it right. It's just you're not saying what I'm looking for. So this is an on delay timer. This is actually a mechanical timer. This is called a dashpot timer. This deal with how fast it takes for a fluid to flow uh, between two diaphragms. Hopefully this works. And then I'll pass it around so you can see it. This is a on delay timer. So this is the coil. And it's got a solenoid. So when I come up here and put a white voltage across this thing, it's going to pull this armature in. And can you see the timer? That didn't click. So something's wrong with this one. I'll pass it around. Let's see if I find another. Now this timer, when I push in the armature, the contacts change instantly. So as soon as I push it in, they change instantly. And then when I let it go, now it's timing. And this one you can actually hear the contacts. So there's no delay when I energize the coil. This times when I de-energize the coil. So that one you're looking at, that's an on delay. This right here is an off delay timer. So we're going to look at non-retentive timers. These would be what we call a non-retentive timer. You can't do a retentive timer with relay logic. We'll also look at a off-delay timer, and we're going to pick up a brand new instruction called the move instruction, which is pretty cool. If we still, we still say, what's the term now? It's not sick anymore, is it? What is it? If it's really neat. Neat still okay. Program timer instruction to interlock each other, and we'll look at how we can cascade instructions and use these timers. So we have what we call fixed timers. Basically, what's the difference between a constant and a variable in a program? So it's not the same in math. So in math we have constants like pi. Pi is a constant, right? You understand that? So, but in programming, constants and variables are a little different. So we have already talked about that, right? What's a constant in programming? This is a number that the only way you can change it is if you change the program. We call those constants. A variable is a number that you can change without changing the program. So you can change it while the program's running. Yeah, it's a constant. That's what it says. Does it spell right? Can. You can't change it. You can't change the time. I understand the problem. Sorry. They don't tell me can't. It's supposed to be change. Thank you. You can't change the time without modifying the program. That was kind of confusing, right? So a variable timer would be one that we can change the amount of time without changing the program. So constants, what's constants for programmers? Constants means you can't change it without changing the numbers here besides just on and off contact. Because the timer, what do you think you're about to specify about the timer? How long it's going to time it, right? That's what we got to specify. So if I put it in there and I don't move it or get it from somewhere else, then it's going to be a fixed timer. The time will be the same until we do what? Until we go into the program and change it. A single input timer, this is what we have. So this is what our 3500 uses. So we enable the timer and start timing at the same time. There's another problem. That's mine. I just did that today. Then a double input timer. This is used by Siemens PLC. The application, by the way, is called S7. They also they have what they call a TIA portal, which I think we talked about that a little bit. I'll have to show you that. I'll look up this little Siemens PLC over here. The TIA portal, everything, all these different applications for RS Logic that I've showed y'all we have to run to do different things. So RS Links, we use that to establish to load the right driver. DHCP, we use that if we're using Ethernet IP. Well, the TIA portal stands for Total Integrated Automation. It means so all these applications is in one application. So we don't have to come in and do all this stuff. It's a lot easier and cleaner to set up. So I'll show you an example of that. They use double input timers. So they have one input that enables the timer, and then we have another one that tells it when to start timing. So RS Logic 500, you do one input. When that input goes through, the timer is enabled, and it starts timing with one input. And when we see it, y'all understand that. So these are relay logic symbols. She took motor controls already. So these are the symbols. We have two types. We have on delay. We have off delay. So what we do, if the arrowhead points toward the switch, it's an on delay timer. If it points away, it's an off delay timer. So we have two contacts. We have an on delay normally open, an on delay normally closed, an off delay normally open, and an off delay normally closed. Are you okay on these? Yeah, all you gotta do is it makes sense, right? If it points toward it, it's a what? On. If it points away, it's a what? Off. Now, this is for relay logic. Yeah. Yeah. So we have two types of timer instructions. This is pretty common on all PLC programming languages at Cyberbinion. We have an on delay and an off delay. The on delay will start timing when rung becomes true. An off delay timer will start timing when the rung becomes false. Everybody understand that? That makes sense? When the rung becomes true, off delay starts timing when the rung becomes false. So when I get out of my car, turn my ignition switch off, right? My lights are still on. I open my door and then I close it. And then after amount of time, my lights go off. So that would probably be an off delay timer. So my door closes, it hits that switch, right? You understand? That makes sense? On delay timers when the timer coil or the symbol for it is energized or the run becomes true. Normally open contacts close and normally closed contacts open when the timer is finished timing. Timer contacts immediately revert to the normal state when the timer accumulator register resets to 0. This guy uses registers a lot. We'll talk about that in a minute. Delay before contact switch when timer turns on. No delay in switching when timer turns off. That make sense? So what I'll do, we'll show you all this. I'm going to use an application that simulates RS Logic's. It's called Logic Pro, which is really neat. Cost about $45 to license for a permanent license, and this means RS Logic 500. But there are some differences, like symbols and stuff like that. So what we have the ability to do is we can bring up a simulator panel. So this guy here's got 1, 2, 3 inputs. It's got 1, 2, 3 output ports. The first input port is in slot 1. The first output port is in slot 2, and then slot 3 is an input. Slot 4 is an output. Slot 5 is an input. Slot 6 is an output. We're going to go here. You've got 3 different symbols you can get. You can put a normally open push button, a normally closed push button, or you can mimic a limit switch, would be like a sensor. So we'll just put a switch up there because I'm just going to come up here and then I'm going to come down, pull down a new rung, and then I'm going to come up here and use a, oops, didn't pull it down, did it? Then I'm going to come over here, and I'm just going to call this input colon 1/1/0, and then we'll come up here and go to our timers, and I'm going to put an on delay here. Now, first of all, what we have to do is we have to assign this thing an address. So you can see the on up there, it's a timer on delay. And so when we look at our, if I can bring these back up, when we look at our project tree, can y'all see the data file used for timers? Can y'all read that? T4. So right now, that's what we need to start off with, T4. Now, this sucker is not a bit file. In fact, it uses 3 words, and I'll show you all the layout. Luckily, it uses symbols to address the things that we need to get to, so we don't have to memorize those addresses. So I'm going to come up here, and I'm going to call this T4 :0, and then I'm through. No bits. In fact, this is multiple words. Then it's got a time base. We'll look at that in a minute. Can y'all see what the time base says? 0.1. Yeah, it's hard to see. And down here, I'm going to put 50 here. Let's put 500. I'll put, yeah. And then this is a little different. I'm going to come over here. I'm going to download it. And then I'm going to go to run. And then over here, I'm online. So I'm going to close the switch. Now watch what happens with the accumulator. So the rung is true, and it did what? It started timing, right? It's going to go all the way up to 500. It's going pretty fast, right? Let's drop back there. I thought I put 50 up there. Let me stop it. Okay. And the plus and minus, the zoom in and zoom out don't work on this simulation, by the way. Okay, so it started timing. And then it got up to 50. And then can you see what happened on the right-hand side? So let's control some contacts with this. So let's go offline. T4 :0/done. and then output colon 2/0. Notice funny, the enter symbols don't pop up on this one, so let's go. So the timer's timing, then it hits 50, timer goes through, and then the output turns on. You know, see the light, simulate light over there. Okay, so when the run went true, it started timing. Now what I'm gonna do is I'm gonna turn it off, and you notice, so off is instantaneous. It only times when you turn it what? On. Y'all understand that? That makes sense? So an off delay timer starts timing when their timing coils are de-energized or the run becomes false. Timers normally open contacts change and normally close contacts open when the timer finishes timing. Timer contacts revert to their normal state when the timer accumulator resets to 0. So we'll look at it in a minute. Let's get there. We have two types of format. We have the coil format, which is used by S7. So if you get into the older S7 software, you'll use a coil format. So it'll look just like an output. I think you put the time on the top, and you give it an address on the top, and then put the amount of time on the bottom. The TL portal allows you to use either the time, either use the block format or the coil format. So our Logic 500 uses what? It uses what we call the block format, which is that square I put up there. Everybody okay? This makes sense. And this is also true with 5000, by the way. With our Logic 5000, which is the newest version of this. Huh? Yeah, we do, but something's going on with my application. It's crashing every time I try to run it. I'm going to have to reinstall it. The preset register. So what does the preset register do? This is the amount of time before you go to a multiplier. I can multiply 1, 50 in there every time for 50 in there, multiply 1 every time for 5 seconds. We got another register called the preset register. That's the number. It's called the time base. It's not in here. The accumulator. I'll have to show you all that next. What's the accumulator? So here's the accumulator right here, ACCUM. Here's the preset register. So I'm going to come up here, is it running? And I'm going to energize it. So the accumulator starts off at what? 0. I'll start this. So the accumulator shows you the current time. Everybody okay? By the way, if it's timing and I reset it, if I make it go false, it automatically resets. Can y'all see that? Before it times out. Guys, y'all go ahead and take a 10-minute break. Y'all wake up, guys. 10 minutes. So what's the preset register? Time you want at the time, right? What's the accumulator register? Yeah, it's the current time, right? It actually shows the time it allows. Everybody okay so far? Okay. Then we have what we call a status register. This is called flags. Holds the address bits that are used by the PLC processor to monitor the status of the timer. There's only three things that it gives us. Two of them are actually visible. And we don't need to know the address because it's given a symbol. We have EN, stands for enable. So notice this status bit goes true anytime my timer is enabled. You'll see that. And it goes false if it's not enabled. So a non-retentive timer is not enabled. The accumulator goes back to what? 0. Yeah, so here it's true. The rung's true. My timer's accumulating time, right? But if I stop it before it's through, it automatically goes back to 0. And notice the enable bit, the enable output went what? False. Okay. We'll turn it on right now. And we're going to let it time out. So it's enabled. It says, okay, you can start timing. When it gets up to 10, I have it set up to time for 10 seconds. It's the end bit, which we call the done bit, by the way, because the timer is done. That's a good name, right? Now, this is a bit inside one of the elements that make this up. It's a book called registers. If you look at the only true registers are inside the microprocessor. These are not inside the microprocessor. These are out in there. So if you read about this in the actual article, the actual instructions in the book, they say every timer has 3 elements to it, 3 words. And one of them is the status word, which tells us the status of the counter. We know 2 of them already, right? We know in there, one of the bits says it's a 1 when it's enabled and it's a 0 when it's disabled. And then we have the done bit. That is a 0 when it's not done, and it goes to a 1 when it's done. And what's nice about it is all this logic is assigned it a name. So you don't have to know the address of it. I'll actually show you where it's at in a minute. So every timer you build, every timer you set up requires 3 words of memory. We have inside the data file, we have 256 of them. So the amount of memory one time, so one timer eats up 3, 256 of them would eat up 3 times 256 words. But then we can set up another timer file down here past 9, right? Past it. So the enable shows us when it's enabled. The done shows us when it's through timing, right? And then we got another one that we'll look at that they'll assign it a name, but it doesn't have a coil coming out on the side, a coil symbol coming out. Are we okay? So the status elements, or the status word, would probably be more correct. It holds flag bits that are used by the PLC processor to monitor the status of the timer. But then we can address those status bits. Timers in Allen Bradley RS Logic 500 PLC use the data file 4 reserved for timer instructions. Some Allen Bradley PLCs allow T data files 9 to 255 to be used for timers. Timers can have an address from T4 to T255. In theory, we can have 256 timers. In practice, the number of timers is limited by the memory capacity. Now, this guy uses an integer. It uses a 16-bit integer. And we talked about this the other day in this class, if y'all remember. So an integer is a signed number without a fraction, right? Now 16 bits, I could have 2 to the 16th combinations. What's 2 to the 16th? Combinations. Now the problem is that we say a watt sign. So how is it going to represent a sign? How's it going to say the numbers minus or numbers in 1? All we got is ones and zeros to work in. So when I write a sign number, where do we usually put the sign at? Over here on the left, right? So we got 2. Well, what we do is we sacrifice the most significant bit. So when I'm dealing with integers, we sacrifice this bit right here for the sign. If we put a 1 in this bit, then it's going to be a negative number. If I put a 0 in that bit, it's going to be a what? Positive. So that means now I can represent numbers up to 2 to the 15th because we're sacrificing a number for the what? For the sign bit, which gives us what? 2 to the 15th. 32,768. Now what that did is it gives us negative numbers. We have 32,768 negative numbers, and we have 32,767 positive numbers. Why do we have one less positive number than we have negative numbers? Because 0 equals wipes out one of your positive alternations. Your positive numbers. So timers can't count backwards. They can only count forward, right? Understand? So that means the maximum number you can put into the preset register of a RS Logic 500 counter timer is 32,767. If you got the number and figure that, it'll change signs and it won't work. Everybody understand that? It uses something called Two's complement, which is really cool, but to represent sign numbers. But that's what we do, basically, just sacrifice the most significant bit. And we'll show you a big problem in counters. This will really pop up in counters. Multipliers, so we have a time base. The time base is a multiplier. So to come up with the actual time, we take the number of the preset, we multiply it by the time base at every time. So here, our logic depends on DLC. How many time bases can we have? So we have a 1, and then what would the next be? 0.1, 0.01, and then 0.001. So we can really short time to this one. I wanted to deal with milliseconds. I wanted to deal with fractions of numbers. I use a multiplier 1. If I wanted to deal with half seconds, like half seconds, I use 25, and then I use this would actually give us that. So this is the multipliers available. So let's come up here and bring up. So I've got RSA. I actually put it on RSA 500, and so here's our multipliers. I got to take it offline. What changes? Oh, yes, I'll say it. So here's the multipliers we have for if you were on the 1,000. These are the multipliers you have. You have a multiplier 1, .01, .001. So how many you have available depends on the actual PLC. This makes sense? So how do you come up with your time? You take whatever's in the preset register, you multiply it by the time base. Let's just leave it in there. No, let's change the multiplier to .01, and then we'll upload it or download it. Woo. See there? So the time, so let's turn it off. Let's see how fast this times. So it's not 10 seconds anymore. It's a tenth of a second, right? Everybody okay? So using the multiplier, we can get milliseconds time on this thing. We can get second time on this thing. The best we can do is in seconds. We don't have any hours. But if I wanted an hour, I would use multiplier 1, right? And then 60, right? Or 60. I'm sorry. 360 times a second. Right? So I'll come up with our actual time. We take what's in the preset register, we multiply by the time base, and then that would give us our actual time on this number. It says the number of time-based multipliers is determined by the PLC model. So I don't know what's available on the 1000s. Don't need to probably look at that. I think it's only got a multiplier of 1 and 0.1. These are the status bits that's available to us. So this is the actual layout of a timer right here. Let's see if I got it. So this is actual. So word 0 would be, so word 0 bit 15 would be your enable. Word 0 bit 14 would be your timer time, and 13 would be your done bit. So word 1 holds your value, word 0 your cumulative. So this is the actual address I go to. So I wanted to get to the enable bit, and I'm going to keep 4, right? I put dot 0, word 0, slash 15. But what they do, make it easy so I know these addresses, is these word names. So ACC is the name for the accumulator. So if I wanted to address the accumulator, I would come up here and that's what I would do. So I'd put T4, then I would put the what? The timer number. We can have from 0 to 255. If I wanted to address the preset register, then I'd say T4, that would be the timer number, and then I would put .PRE. So I don't have to know it's word 15. I mean, I don't have to know it's word 0, 1, or 2, right? You understand that? All I need to know is know the name of these registers. So the bits. So getting into our status register. My pen stopped working. So getting into our status register, what we'd have to do is, let me go back. Dang it. We would use, I'll try to do this with my mouse, guys. My pen stopped working. I'd use T4, then I'd put a what? A colon, and then I would put a timer number, 0, and then I would put a slash done, and then that would give me my done bit. So here we're going through the whole thing. This is the data file number, this is the timer number, and I use a dot indicating a what? A dot indicates a what? I almost got it written out in a word. A slash indicates a what? A bit, right? So this makes it a little easier on us. I don't have to know that. I don't have to know the registers. I don't have to know where they are. All I got to do is specify. If I want to address the accumulator, I'll put dot ACC. If I want to address the recent register, I put dot TRE. If I want to address the done bit, I put slash done. If I want to address the enable bit, I put slash EN. If I want to address the timer timing, which indicates it's timing, right? I put slash TD. So let's add the timer timing bit to our program. So I'll go offline. And so they don't show us, they don't give us an output over here for the timer timing. But I will stick a rung right in here. Oops, where'd it go? Oh, it gave me a down drop. We'll stick a rung right here. And then here we'll use the timer. So I'm going to put T4 colon 0 slash timer timing. Everybody okay? Okay. And then I'll come up here and I'll put a coil out here. And I'll assign it to an output. Let's change our multiplier back to 1. Or we won't be able to see it, right? Then check for errors. Looks like everything's clean. Download. So I'm gonna, let's see, switch 0. Turn on switch 0. Notice what happens here. Okay, so this indicates it's timing, right? And then when it finally gets up to 10, the done bit should go true, and the timer timing bit should go false. So the timer timing bit is going to show us when the timer is timing. The done bit is going to show us what? So a non-retentive timer, this is what we're looking at right now. We have 3 different types of timers. We have a non-retentive timer on delay. We have a non-retentive timer off delay. And then we have a retentive timer on delay. This means the timer times when the runs true, when the runs go false. It keeps its value. This guy right here, we don't have to do what with it. We have to reset it. So I'm going to put y'all okay. If I don't put contacts up here, we can see it timing now, right? So let's go back and stick a rung into our program. Go offline. And we'll time them from the same thing. And then we'll insert a rung right here. And then I'll come up here and I'll reuse my start. And then I'm going to bring down, I'm going to go to my timers in my timer tab, and I'm going to bring an off delay timer in. And we'll call this T4:1. And we'll give it a name timer 2. Then it's asking for a multiplier. We use that preset. We'll use the same preset. And then I think we're ready. Check for errors, no syntax errors. Okay, so my top one is a on delay timer. My bottom is a off delay timer. I'm going to switch one. Notice the enable and the done bit. When it's true, we're back with this number. So anything I want to do while this time is so my other one says it's done. Now I'm going to turn it off. The top one's going to clear. And what did my bottom start doing? So off, this guy started timing. When it's true, that guy starts timing. So y'all see the difference between an off delay and an on delay. So an on delay, contact by an on delay. We'll do what? They will go after time. Off delay. As soon as you can identify the off delay, your context will change. Everything else is fine. What's the preset? This is what you want to time from, right? What's the later? Oh, the current value, right? What's the time base? It's a multiplier. So to get your actual time, you take what? You take the time base, multiply by the preset, and that'll get you the actual time of the timer. Okay. So we'll put another rung in here. We'll control it by the same input. We'll come up here and put a timer. I'm going to put a retentive timer out here. So start. We'll call this timer 3, T4:3. We'll put a time of 10. And I think we're okay. So I close 0. Timer. I should have used timer 2, but that's okay. Your 2 timer, your 10 timer starts timing. Your on play starts timing. This guy right here is not timing yet. This is on play. Got 10, both of them done. Okay. turn switch 0 off. What happened? This guy did what? This guy didn't. So I'm going to, what can I do now? What does it say we got to do? Must reset it. Okay, so let's go offline. See that instruction right there? You see what it says? It says RES. What do you think that stands for? Reset. So we'll put a rung right here. And I'll give it another switch. Y'all want to reset it when this timer right here goes false? When my off delay goes false? We can do that. T4:1 / done. And then over here we'll pull down the reset instruction. And which timer do we want to reset? 3? Yeah. So we got any errors? So the way this should work is that this is going to come up, this is going to time out. When we get this guy to start timing, then when this guy here times out, it should automatically reset this guy, right? By the way, I changed my Ethernet from the original setting, so that's why I'm getting that small little arrow at the end. Okay. Oh, sorry. This guy, the done bit, comes up true right off the bat, so we're going to have to make this. So right click, change instruction. Change instruction. We'll change this. I'm going to show y'all something real cool in a minute. Change it over. So this is what I wanted to show you. So if I come up here and turn this one off, what does it do to the time? This top one, can y'all see? It resets it to what? 0 before it times out. If I come over and do this one, sorry, if I come over and do this one, I'm going to change this to a switch too. I don't know why. So let's change this to a switch. Because somehow I got these things intertwined with each other and they're not doing what I want them to do. Okay. So when this guy's enabled, this is the on delay timer. And if I disable it, it does what to the accumulator? Yeah, can y'all see that? I'm going to come over here and bring switch 2 true. And notice what happens on this one when I disable it. What did it do? What? Okay. So right now it's disabled. The enable's gone false. And what did it do? Because this is a what? So what does retentive mean? It holds the time, right? So up here on this first one, this is a non-retentive timer. So if I started timing, I'm gonna if the enable goes false, what does it do? Resets the accumulator, right? So if it goes false before it times out, it's going to reset it. Or if I let it time out, then the done bit will go true, and then I'll have to then it just stops, right? So how do I reset the first one? The top one. I have to go false, right? On this one, when I stop it, what does it do? It holds its time. Now it's went true. Now what do I have to do to this guy? Yeah, I have to reset, right? And then it goes back to what? 0. So a retentive timer holds its time until you reset it. A non-retentive timer will automatically reset anytime it goes off. Does that make sense? Okay. Any questions? So that's the 3 types of timers we have, guys. So on delay, everybody's okay on the registers, right? First of all, we have to assign it an address. So we have, right now we have T4 is 0, and what's the highest we can go on timer off is T4. Okay. Questions? What is time to do? We're going to county counter down time stuff. What is time to do? Find out actual time. The move instruction. This is an output instruction. This is an extremely powerful instruction. And copy it into any data folder. So it's called move. Technically, move means you move it, but I have to move it. Copy any word. No word this. It works with words. We'll copy it from any data file over to any data file. Data file, the words we're going to be dealing with, of course, is the accumulator and the preset. Now, this is extremely powerful. The book does do a really good job with this. You to copy the contents of one 16-bit data file into another, or for other timers, data registers, or data files. Basically, the only two we're looking at is the preset register and accumulator register. So we can use these to create variables. So can y'all see this? I can't make it any bigger. What figure is this in your book? So we're in timers. Y'all find it in the book so y'all can see it better than me? Because this turns out really tiny. What figure is that? I can't. Can I go back to? Right? Okay. Oh, I know what you're doing. You're looking for the figure, right? Eight dash 10. 8-10. You got it, Derek? It's different in your book? Four. I'm trying to find my slide. I'll just put a blank slide in here. So they're saying, dang it, Rich. I'll take a break. Let me see if I get my pen working.